In assignment 2, the task was to explore support vector machines along with kernels and dimensionality reduction. SVM is a principal method in terms of optimization related foundations and is predominantly used in a kernelized form. The beauty of the kernel trick is that it enables us to use a linear classifier in a feature space that is non-linearly related to the input space without needing to explicitly access that feature space or transform the data. While kernelization enables the SVM to learn decision boundaries which are nonlinear in the input space, the use of slack variables, i.e. regularization, makes it effective for datasets which are non-separable. In stage 1, I explored how cross-validation is used to tune hyperparameters in order to ensure that the model does not overfit. C is a trade-off parameter. It controls the importance given to two conflicting goals in the objective function that SVMs try to minimize or maximize depending on whether the problem is being solved in the primal or dual space. The two conflicting goals are maximizing the margin, i.e. minimizing the norm of the W parameter, versus penalizing examples that fall within the margin. In other words, ensuring that most examples have functional margin at least 1. If C is high, the margin will be narrow and very few examples will violate the margin constraint. C also trades off error on the training data with the generalization properties of the SVM. If C is very high, the number of misclassifications on the training data will go down, but that could come at the expense of the classifier's performance on unseen data. The bar chart here shows the impact of C on the cross-validation accuracy of linear kernel SVMs. The training data used for all the experiments involving cross-validation is a randomly drawn 10,000 set from the MNIST dataset. The values of C and gamma in the case of the RBF kernel later are typically varied in an exponential manner. For linear kernel SVMs, the parameter value 1, which is the default parameter value, works best. Now let's turn our attention to nonlinear kernels. The gamma parameter can be seen as controlling the extent of influence that a single training example has. Its low values mean far-reaching influence. To efficiently search the space of these hyperparameters using cross-validation, I've used a coarse to fine strategy. In the first pass, the likely search space is swept coarsely, i.e. using a high step size. Here the idea is to get in the proximity of the best configuration of hyperparameter values. In the second pass, a smaller space centered around the best performing configuration obtained in pass 1 is explored using a small step size. In the RBF kernel case, in the coarse pass, the value of gamma was varied from 2 raised to minus 9 to 2 raised to minus 1, and C was changed from 2 raised to minus 3 to 2 raised to 5. The best C gamma tuple that was found at the end of the first pass was 2 raised to 5 and 2 raised to minus 5. So the fine grid search, meaning the second pass, was centered around that. The best overall values of C and gamma are 2 raised to 4 and 2 raised to 5. The table here validates that the C gamma values corresponding to the best cross-validation accuracy also perform well on the test data. Similarly, C and degree values are tuned using cross-validation for the polynomial kernel SVM. Note that because of the computational limitations of my machine, especially for kernels like chi-square, for which n cross n computations need to be done for supplying the K matrix, and to ensure the use of the same data for all similar experiments, a randomly picked 15,000 subset of the MNIST training dataset is used for all experiments that follow. The random subset selection is pseudo-random in order to ensure apples-to-apples comparisons. The test data subset is picked such that the train to test ratio is maintained. For the USPS dataset, the entire data is used. Now let's look at the results for different kernels and classifiers. Here you see confusion matrices for the RBF kernel SVM and the corresponding true positive rate, and so on and so forth for different kernels and classifiers. This figure compares the accuracies obtained using the linear kernel SVM, RBF kernel, polynomial kernel, chi-square, 1NN and 3NN. As expected, nonlinear kernels like RBF and polynomial kernels outperformed the linear kernel. The performance of nearest neighbor classifiers exceeded the expectation. The difference between the accuracies of 1NN and 3NN was fairly small. The best accuracy was achieved using the RBF kernel SVM. One of the dominant misclassification patterns is 3 getting misclassified as 8. This is obviously consistent with our intuition visually, and the confusion matrices show that using RBF kernel SVMs, we can substantially suppress this. Now let's compare liblinear with libSVM with a linear kernel. When the use of nonlinear mappings gives no performance boost, we should consider using liblinear since it's typically faster than libSVM with a linear kernel. Classification using SVMs requires a quadratic programming solver. The solver used in libSVM is targeted to work for both linear and nonlinear kernels. The solver in liblinear, on the other hand, is targeted to primarily work with the linear kernel. Plus, it offers several variations such as L1, L2 regularization, L1, L2 loss, and so on. The table here shows that the accuracies achieved using the two are very similar, though here libSVM slightly outperforms liblinear. Liblinear does not use the bias term B by default, but by setting B to 1, the bias term can be added both to the loss function and the regularization term. Doing that may cause the accuracy difference between the two libraries to be smaller. Another potential factor is that libSVM uses the 1 versus 1 strategy for multi-class classification, whereas liblinear uses 1 versus the rest. Moving on to stage 2, what are additive kernels? Additive kernels are those where the comparison function, meaning the kernel function, is a linear combination of functions of xi, yi input pairs. Two examples are the intersectional kernel, which is defined by the sum of the minimum of xy pairs, and the chi-square kernel. Additive kernel SVMs are interesting because they can produce improvements in accuracy over linear SVMs for various problems while having almost the same runtime. That makes them attractive for large size datasets. We now explore various dimensionality reduction techniques. In PCA, I used the top k eigenvectors for transforming the data, where k was chosen such that the sum of the top k eigenvalues divided by the sum of all eigenvalues is greater than or equal to 0.95. In other words, the selection was done so as to retain at least 95% of the information. Unlike PCA, which is an unsupervised method, LDA takes into account labels. Applying LDA directly on the raw features led to some numerical issues in my case, possibly because of metric inversions. To rectify that, I fed the PCA transform data to LDA. Since I retain almost all of the information in PCA, using it as a pre-processing step to LDA does not affect LDA's performance. Another dimensionality reduction technique that I explored was kernel PCA. Standard PCA performs linear dimensionality reduction. If the data has more convoluted relationships which can't be represented in a linear subspace, PCA won't work well. Kernel PCA generalizes the standard PCA for nonlinear dimensionality reduction. In my experiment, I looked at how well a very low dimensional kPCA representation holds up. This bar chart looks at the accuracies achieved using various feature representations. Raw features, PCA, LDA with 153 dimensions, LDA with 100 dimensions, LDA with 9 dimensions, and kPCA with 15 dimensions. Now let's look at some qualitative analysis. The first set of images that you see are images for which PCA leads to correct labels, but raw features don't. The second set has images for which raw features lead to correct labels, but PCA doesn't. There are many such other categories which can be looked at in the report. The confusion matrices show that the dominant misclassification patterns include 9 getting classified as 4 and 7, and 5 and 8 getting classified as 3. These patterns clearly tally with the visual similarities between the digits. Both PCA and LDA representations, despite their reduced dimensions, produce good accuracies similar to that of the full raw features. The LDA representation was able to produce nearly 81% accuracy with just 9 dimensions, and KPCA led to 83.5% with 15 dimensions. On to stage 3. When the data contains nonlinear structures in a low dimensional space, techniques like PCA don't work because they are linear in nature. IsoMap performs well in such scenarios when the data points lie on a low dimensional manifold. The last step makes multidimensional scaling (MDS) a special case of IsoMap. These are Euclidean distance based IsoMap clusters for digits 1 and 7. As you can see, they are quite well separated. Digits 4 and 9, on the other hand, are not that well separated. This is a Euclidean distance based IsoMap plot for all the digits. These are IsoMap clusters for 1 and 7 computed using the tangent distance. This is all the digits using the tangent distance. Notice how the actual images are superimposed on all of these plots to give better insights. Though 1 and 7 get separated using both the distance metrics, in the tangent distance case, the distance between the means of the two clusters is much higher, meaning that the extent of separation is better in the tangent distance case. Similarly, embedding sets of digits 4 and 9 are better, though not fully separated, using tangent distance than using Euclidean distance. Stage 4 deals with SVM parameters that affect computational needs. Before analyzing parameters, a couple of other factors are mentioned. The first is the number of data points, n. SVM's training time complexity ranges between order n square and order n cube for large values of n. Another parameter is the number of support vectors. The test time complexity of SVMs is linear on the number of support vectors. Now let's focus on the parameters of SVMs and kernels. The first is the kernel type. The more complex the kernel, the greater the training time. Hence, the linear kernel is lighter than RBF. For high values of C, the training time goes up, though I haven't been able to observe these for the experiments on MNIST and USPS datasets. Another parameter is the degree of the polynomial. As the degree parameter is changed from 2 to 9, the training time and the testing time go up. The second table shows that the gamma parameter has no bearing on the computational aspect. Next, we explore an iterative training scheme in which you initially train with only 10% of the training data. Then the model is applied to the rest of the training data. If there are any misclassified samples, they are added to the set used for training in the next iteration. For linear SVM, this iterative scheme lasted 7 iterations. At the end, around 28% of the original data was chosen as the final training subset. The ratio of the number of support vectors in the original data and that in the subset selected is 0.75. In the RBF case, an even smaller percentage of the original data was chosen as the final training subset. What is the advantage of doing this iterative training? Since the memory requirements of SVM training algorithms are a function of the training data cardinality, training an SVM on very large data sets involves a huge amount of memory. Therefore, it's essential to find a way to decompose the problem. What is desired is to find a subset of the data that can fit into the memory and is big enough to contain almost all of the support vectors. In each of the iterations, the size of the data used for training is much smaller than the input size. Hence, the memory needed by training is less likely to exceed the system memory available. The downside is that because of multiple iterations, the overall training time is higher. And since not all support vectors from the training data are guaranteed to be contained by the subset finally chosen, this scheme's classification accuracies are lower.